Welcome to this video lab, where we're going to be performing Experiment 8, the copper cycle. Starting out, the purpose of this lab is to perform a series of reactions on metallic copper to convert it to 4 different copper compounds, before reverting it back to its original metallic form. During the lab, we will perform a series of precipitation, decomposition, acid-base, and redox reactions, before calculating a percent recovery based on the final copper product. Copper is a highly versatile transition metal found in the D block elements of the periodic table. Copper is used for a wide variety of modern-day applications, including electrical wiring, plumbing, electronics, and jewelry. Copper can have a variety of oxidation states from -2 all the way to +4, but most commonly copper is found in its +2 oxidation state. In this experiment, we're going to convert copper through 5 successive reactions to produce 4 different copper-containing compounds, before ultimately recovering elemental copper. The experiment utilizes a variety of different kinds of reactions, so let's discuss each of them. First off, precipitation reactions, also sometimes called double displacement reactions. These are when 2 reactants dissolved in solution react to produce an insoluble solid product. The driving force of the reaction is based on the solubility rules of the ionic compounds. The strong attraction between the positive and negative ions in solution causes the formation of a precipitate. Below is an example showing the reaction between potassium sulfate and lead nitrate being mixed to form insoluble lead sulfate. The next type of reaction is acid-base reactions, also referred to as neutralization reactions. In these reactions, an acidic solution reacts with a basic solution to produce some constituent ionic salt and water. The driving force is the reaction between the acidic hydrogen protons and the basic hydroxide anions. Below shows an example reaction between hydrochloric acid and sodium hydroxide to produce sodium chloride and water. Decomposition reactions are where a reactant is broken down into one or more products when subject to specific conditions. The most predominant driving force of decomposition reactions involves the application of heat, as seen below, where potassium chlorate decomposes into potassium chloride and oxygen gas. However, there are many other forces that can cause decomposition, including light, electrolysis, humidity, or acidic environments. Lastly, this lab involves the use of redox, or reduction oxidation reactions. These are reactions that involve the transfer of electrons from one reactant to another, causing the oxidation state of 2 or more atoms to change. The driving force of these reactions is that electrons are transferred from an atom with a lower electron affinity to an atom with a higher electron affinity. Oxidation is the process by which a reactant loses electrons, and reduction is a process by which a reactant gains electrons. Now that we've discussed some of the background for the lab, let's discuss the safety concerns for this experiment. Nitric acid, hydrochloric acid, sulfuric acid, and sodium hydroxide are corrosive to flesh and can cause skin burns, so gloves should be worn at all times when handling them. Similarly, these same reagents are also highly exothermic upon contact with water, so these reagents should also be handled with caution and added slowly. Nitrogen dioxide is a toxic brown gas that can be fatal upon inhalation, so these reactions should be performed in a fume hood with proper ventilation. Now let's get into the experiment. These procedures were performed by James Speller and Jacques Reyna. To start off, we measure the mass of a single copper wire before placing it into a clean 250 ml beaker. The mass of this copper wire was 0.4409 grams. The initial copper wire was about 4 inches long, had a shiny tint with a reddish-brown color. Next, to the beaker containing the copper wire, we add 4 milliliters of 16 molar nitric acid. Immediately upon addition, we can see the wire reacting with the acid to produce a yellow-brown colored gas. This is highly toxic nitrogen dioxide gas. As the wire continues to react, the solution becomes a clear green liquid. However, upon swirling, yellow-brown gas diffuses out of the liquid. The beaker is also slightly warm to touch. After about 10 minutes and ample swirling, the final solution is a vibrant, clear blue color. The reaction is finished because there is no more copper wire and no more production of the yellow-brown gas. Now that the reaction is complete, We dilute the solution by carefully adding approximately 150 milliliters of deionized water. The final solution after the first reaction is a clear light blue solution containing our copper nitrate. For our next reaction, we're going to measure out 30 milliliters of 3 molar sodium hydroxide into a 50 milliliter graduated cylinder. With the 30 milliliters of sodium hydroxide, we're going to slowly pour it into the copper nitrate solution while stirring with a glass stir rod. Immediately, we see a color change as the clear light blue solution becomes a cloudy dark blue solution due to the formation of copper hydroxide. The beaker also becomes slightly warm upon addition of the sodium hydroxide. To ensure the reaction has gone to completion, we check the pH to make sure it is completely basic. The blue pH paper indicates a pH around 11 or 12. For our next reaction, to facilitate the decomposition of copper hydroxide, we're going to add a magnetic stir bar and place the beaker on top of a hot plate. We place a watch glass on top of the beaker and turn on the stirring and heating. The initial solution is a cloudy blue color. Over time, we can see this color gradually begin to darken. Eventually, the solution becomes completely black with no more hint of the blue copper hydroxide. After about 20 minutes, our final solution is a cloudy black color before we take it off the hot plate to settle. After taking off the hot plate, we can immediately see the insoluble copper oxide settling to the bottom of the beaker. And over time it separates enough that we can decant off the top layer of water. To decant off the layer of water, we're going to gently pour the liquid down a glass stir rod into a waste beaker. A glass stir rod is used during decanting to prevent splashing. We also pour very carefully to prevent the loss of any copper oxide product. During this first decantation, we poured off about 100 milliliters of liquid. Next, we're going to wash the solution with two 100 milliliter portions of hot water. So on the hot plate, we add approximately 200 milliliters of water into a large enough beaker and heat until just below the boiling temperature. When the washing liquid is ready, we add approximately half to our beaker containing our copper product before stirring and then letting settle. After letting settle, the solution is again decanted off, followed by another washing with the final half of the hot water. The primary method of decantation we used was the pour-over method. However, there are two other methods that can be utilized as shown here. This is the stir rod on top method, where the glass stir rod is held over the top of the beaker and liquid is poured out of the spout down the rod onto the edge of the waste beaker. Another alternative is that you can utilize a plastic transfer pipette to very carefully pull off excess water. After all of the washing and decantation, our final liquid solution is clear and colorless, with the black copper oxide product suspended near the bottom. From our waste container, we can see that some of the copper oxide was decanted off. However, this amount of loss is generally expected for this lab, as some of the particles were too small and would take a very long time to actually settle to the bottom. For our fourth reaction, we measure out 15 milliliters of 6 molar sulfuric acid into a 50 milliliter graduated cylinder. To our beaker containing the isolated copper oxide, we gently pour in the sulfuric acid while continuously stirring. After stirring thoroughly, we can see the final solution is a clear light blue solution of copper sulfate. The beaker is also slightly warm at the end of the reaction. For the last reaction, we take the beaker containing our newly formed copper sulfate and place it on the hot plate. To the beaker, we add a piece of aluminum wire that we gently bend into a circle so that it fits inside the beaker. Next to our solution, we add in approximately 5 drops of hydrochloric acid to act as a catalyst and help start the reaction. We can see the reaction has started due to the formation of copper metal directly onto the surface of the aluminum wire. Because the reaction depends on fresh aluminum, we turn on the stirring to help agitate the aluminum wire and expose the aluminum metal beneath the newly formed copper. We also turn on some gentle heating. This heating is actually not necessary for the reaction to proceed, but it does help speed up the reaction. We also add a watch glass to the top of the beaker to contain any fumes. Over the course of the reaction, we can see the formation of copper on the surface of the aluminum wire. The stir bar agitates the wire, hitting off pieces of copper, which allows new copper metal to form on the freshly exposed surface. And over the course of about 20 minutes, the solution goes from a clear light blue color to a cloudy gray-brown color. We know the reaction is done enough when we see no more blue color from the copper sulfate. Next, we remove the beaker from the hot plate to let the solid settle to the bottom. We can also tell the reaction is complete because on the surface of the aluminum wire there's no more formation of copper metal. The wire continues to bubble due to other side reactions between the aluminum and sulfuric acid, which produces hydrogen gas. Before isolating our final copper product, we remove the aluminum wire and magnetic stir bar. Here's the final solution containing our copper metal product settled at the bottom. To isolate our final product, we're going to gently decant off the excess liquid on top of the solid. Here's our solid after pouring off most of the excess liquid. Next, we're going to transfer our product to a small evaporating dish. However, before doing so, we must measure the mass of it for future calculations. Here we can see our evaporating dish has a mass of 22.9661 grams. Now that we have the mass, we can transfer our solid into the evaporating dish using a wash bottle. taking care to transfer as much of our solid product as possible. Very carefully, we are now going to pour off the excess water and then wash the solid 3 times with approximately 5 milliliter portions of deionized water. We decant off the excess water between each wash. Here is the copper after washing with water. We can see that it is still very wet, so to remove the excess water, we're going to wash it with 3 5 milliliter portions of ethanol. Following the same procedure as before, we wash the copper product 3 times with ethanol, taking care to decant off the excess ethanol between each wash. Next, we are going to dry the product fully, so to do this, we prepare a steam bath on the hot plate. To prepare the steam bath, we take a 100 milliliter beaker and add approximately 75 milliliters of water. We turn on gentle stirring and heat the liquid until boiling. After boiling, we place the small evaporating dish over the bath and observe the drying of the product. We can see the ethanol readily boiling off as we heat the product until completely dry. We know the product is fully dry when we can gently shake it and the product does not stick to the evaporating dish or clump with itself. Now that our copper metal is fully dry, we can finally weigh our final product and calculate a percent recovery. The final mass of our product, with the evaporating dish, is 23.2578 grams. This mass, subtracted with our other evaporating dish mass, gives the mass of our copper product to be 0.2917 grams. To calculate the percent recovery of our product, we take the final mass of our copper divided by the initial mass we obtained at the start of the lab. The initial mass of our copper was 0.4409 grams. Completing the calculation, this gives our percent recovery to be about 66.16%. Our recovery is a tad low, and we can see by looking at our waste container a fair amount of the copper product was decanted off with the washing steps. This could have been prevented by being more patient to let the solid settle before decanting off the liquid. Another common source of error that in our case did not occur is the oxidation of metallic copper into copper oxide. Copper oxide has a higher molar mass than metallic copper, which can cause your final percent recovery to appear higher than it actually is. In this picture, we have 2 pieces of copper wire. On top, we can see the fresh piece of copper wire that we used at the start of the experiment, and below it, we can see a piece of wire that has sat out in the presence of oxygen for a while. The oxidation causes the wire to lose its luster as the metallic copper on the surface passively reacts with atmospheric oxygen to form copper oxide. The oxidation process can also be sped up through excessive heating. With this, the experiment is completed, as we have successfully recovered our metallic copper. To clean up, we dispose of the liquid waste into a designated plastic carboy, and the solid waste into a designated solid waste container. We rinse all the beakers thoroughly and return all the equipment to their proper storage locations. We successfully converted metallic copper to multiple copper compounds through a series of precipitation, acid-base, decomposition, and redox reactions before finally recovering metallic elemental copper. Thank you for watching, and be sure to answer all of the following post-lab quiz questions.